To the 8th edition of the NLP Breakfast, hosted by Fiddly in our Redwood City office. My name is Edward, and I'm an NLP engineer, and today we'll be talking about the topic of knowledge distillation in light of the recent Stanford's publication, BAM, Born Again Multitask Networks for Natural Language Understanding. We'll also discuss the findings of 3 of the earlier references about the topic. The architecture of this presentation is that we're first going to wonder why we need knowledge distillation, and that will lead us to introduce the teacher-student paradigm. Then after introducing the mathematical problem formulation, we'll talk about 2 applications of knowledge distillation, in particular in a smaller network, a smaller bi-LSTM network, and its application to multitask learning, which is the subject of the Stanford paper. So most of today's best performing algorithms either belong to one of these categories. The ensemble model, which aggregates predictions from algorithms of very different nature, be it linear, decision trees, SVMs, and so forth, and deep learning algorithms, which have a tendency to get bigger and deeper every year, like in NLP, the recent Elmo, BERT, or XLNet. Models in both of these categories suffer from a very long inference time, which make them impractical to use in production. So instead of proposing yet another model architecture, knowledge distillation aims at leveraging the prediction power of the best performing models that we will call teacher into effectively teaching a smaller network that we will call the student. And this student is effectively better suited for production. So now I want to explain the major difference that there is with transfer learning, and it's in 2 points actually. First of all, in transfer learning, we're usually working with similar model architecture. And we talk about shared layers between these models. And what we do essentially is copy all the weights from one model to another. Whereas in knowledge distillation, the student can be fundamentally very different from the teacher in terms of model architecture. And the second point is that what the student is going to imitate is the output of the teacher only. So the latest layers in the neural networks. To get a good intuition of how it works, let's consider the supervised classification setting of the MNIST dataset, where we try to classify images of digits. The way you train a model is by minimizing an objective that associates to each data point, so each image, a single label that we usually say is one-hot encoded. But what we're implicitly doing when we're doing that is saying, I'm 100% confident that this number is a 7, and I want my model's parameters to learn that very confidently. But even though we eventually want our model to distinguish between these very close numbers, we might be better off by saying, well, actually, there's 90% chance that this digit is a 7, but there is a good 10% chance that it's also a 1. Indeed, if you want your model to learn that it's a 7 no matter what, you might be impairing your model's ability to eventually recognize a 1. And so that's what knowledge distillation is about. It's a regularization technique that takes the teacher's prediction power on a model that might not benefit the the transfer learning or the fact that we're using multiple models to have this additional regularization. And so another overview of knowledge distillation, abbreviated KD, is to say, for instance, let's say we have a sentiment classification data set, movie sentiment classification data set. We will train our teacher with these regular one-hot encoded labels. And after training, provided we have a good validation score, we'll produce the prediction for the same inputs that we will in turn use to train our students. Now there's an additional interesting catch to it. It's that if you have additional unlabeled data, you can also, after training of the teacher, predict them so that you'll perform data augmentation and that you'll have additional data to train your student network. Now, as I mentioned earlier, so we're going to slightly change this usual representation of the objective. So this is a representation of a neural network in which at the last layer, so the last layer is the softmax here. And we're trying to match the output distribution, the parameterized output distribution, with the one-hot encoded labels. But now, in the case of knowledge distillation, we use instead the teacher's predictions. And how it translates in the cross entropy is very simple. You just replace this term, which is usually a one-hot encoded variable, by all of these soft targets from the teacher. And so this becomes the loss of the cross entropy in the case of knowledge distillation. Now, an interesting point raised by the first paper about knowledge distillation is that we want to learn that there's a close relationship between digits that are close together, the 1 and the 7, but we might not be interested in learning all the residual probabilities here. And so that's where the discussion of the paper introduces an extended version of the softmax. So SI is what you want to learn in your model, is the parameterized output of your model. And if you write what it's worth, you have this formula. And if you pay close attention, it's not the softmax we're used to, because it's got an additional parameter of temperature, T, here, that has some importance in the output distribution that you have here. Because these are real numbers, and this all sum to 1 and are a probability distribution. And to see the impact of this hyperparameter, we can look at the extreme values. If t tends towards infinity, your transformation of the logit layer will transform your logits into a uniform distribution, so you extract no information from these logits. And if t tends towards 0, you have a one-hot encoded variable for the highest logits, so an overconfidence in your logits. And what the paper argues is that for lower values of the temperature, you can avoid fitting on these residual probabilities that we don't want to learn. So now it's great. We've seen that we can change the usual cross-entropy formulation and to perform knowledge distillation. But there's actually a second way of transferring knowledge from the teacher to the student. And it's simply, instead of trying to match directly the prediction, trying to look at the layer just before the softmax, so the logits layer, and trying to match this part. So if we zoom in for the teacher and the student, actually the last part of the transformation process of your outputs is this softmax layer, and we can either decide to match the last layer with the cross entropy, or we can try to match directly the logits layer. And this second point of view is brought forth by my second reference, which says that the new objective function is going to be an interpolation between what we've just seen, the cross entropy, the knowledge distillation cross entropy, and this criterion, the mean squared error criterion between the log hits of the teacher at the layer n-1. And they show experimentally that the best results are obtained for alpha equals 0, so the loss is only the mean squared error. The experimental setting for this paper is to distill the knowledge from a BERT network into a bi-LSTM. And though they're very far from the results of BERT, so here the results is number 6, they show that for 3 different implementations of the same regularly trained bi-LSTM, they achieve a consistent 3% increase in accuracy, which is a good case to advocate for the power of knowledge distillation. Now, if you're willing to trade that accuracy for faster inference, you're in luck because the bi-LSTM implementation is actually 400 times faster. And why is it faster? It's because it's got less parameters, and there's 1 million parameter in the bi-LSTM, and in the BERT large you have almost 400 parameters. And if you're wondering like me how you can have like 1 million parameters in a simple bi-LSTM network that looks like this, just remember that the LSTM cell in itself has 4 nonlinearities, each of which correspond to an input times output matrix in terms of shape. It's a bidirectional, so you can multiply that by 2. And since in the LSTM cell we're concatenating the input size of the embedding with the cell state, it's usually an additional factor 2, so it's 16 times the usual input times output shape. So now we've seen an application of knowledge distillation that provides a faster inference time by using a smaller network and leveraging the prediction power of the BERT teacher. But there's another application of knowledge distillation to multitask learning. In the multitask learning setting, you have a bunch of shared layers with contextual embedding, and then you perform multiple tasks on top of it, like single sentence classification. So there is the sentiment classification dataset, there is the sentence acceptability dataset. There are also some pairwise text similarity or pairwise text classification, like recognizing textual entailments or natural language inference, or the CROA question pair datasets, and also pairwise ranking between questions and answers. And so in all this, this third reference that I'm introducing is leveraging knowledge distillation and uses the same BERT architecture as the lower layers. But what we're interested in is the actual training process of this multitask pipeline. So this is quite a dense representation. So I'm going to go slowly. The first thing that you're going to do is you're going to train teachers on each of these individual tasks, and a teacher in itself has the same shared layers at the beginning in the same pre-training setting, but the latest layers can be different neural networks that you average. This is in order to produce better predictions using this ensembling technique to the students in the end. So after After you first train the teachers on each of these tasks individually, you provide predictions for this same data set. And now your student is going to learn from these predictions, but on all the tasks simultaneously. And once you've trained this objective, there is a last part which gives the best results and consists in single task fine-tuning the student on each of these tasks at the end, separately. So there are two, in the first table they give, there's two things to compare here. The first is the multitask deep neural network. If you compare it to BERT, the only thing you have to note is that indeed doing multitask learning helps the single task's performance. But the big comparison that is quite interesting is that if you use the training with the knowledge distillation trick, you gain an average score of 1.5 in all the tasks combined. And so now we are going to talk about the comparison between the process we've just seen and what the Stanford paper is talking about in its born-again multitask networks. So the reason why it's called born again, first of all, is because we are going to use exactly the same architecture in the student than with all the individual teachers. So in particular, we're not going to do ensemble training for each of these individual teachers like in the previous paper. The second thing is that between the task 3 and 4, we're going to interpolate. We're going to, at the beginning of the training, say, okay, your loss function on which you optimize, focus on the teacher's predictions. And at the end of the training, and that's why this slide is called the student becomes the master. At the end of the training, forget all your teacher's prediction, which you will have used in the early training for better regularization, and try to learn again from the regular one-hot encoded labels. And so this technique is called annealing. So throughout the training, the lambda is going to go from 0 to 1. And so that is one of the other difference between the two papers. And the last difference is that if you've paid close attention in the picture before, there were several arrows here because there was this single task fine-tuning step. And here they argue that, which I will explain in a further slide, but they argue that we should not do that, and we can train on all the tasks at the end simultaneously so that we only have one model eventually and not different models. So in terms of results, because they're not using the ensembling technique for training the teacher, and because they're training on all of the tasks at the same time at the end, they do a bit worse. They do much worse than the paper I just mentioned before that used knowledge distillation in multitask deep neural networks. But compared to most of the methods above, what they argue is that indeed they have this advantage of saying that fine-tuning is actually defeats the purpose of multitask learning, because the result of the training is one model for each task instead of a model that can perform on all the tasks. So the results are not exactly comparable. And what they also show is that so when they try to do single fast tuning at the end from their model, the difference in score isn't that significant, which argues for having the same model on all the tasks. Another thing that I like in this paper is the Ablation Study, which is a table we don't have all the time, but which argues for the fact that they are using layer-wise learning rates. Otherwise, it would decrease a bit the score. They use some task sampling trick, and they show that if they, instead of teacher annealing, if they fix lambda to 0 or 0.5, they achieve also poorer results. Okay, so before we go to the conclusion, last small experiment I want to talk about is this blog post reference, which says that you can distill BERT in your logistic regression. And it's a very concrete application of knowledge distillation, no longer to multitask learning, but we're back again to trying to have a smaller model eventually. So you'll have the movie reviews sentiment classification dataset, from which you will take 1K sentences for the train and the test, and you will also take 5K from the train and suppose that they're unlabeled. This is to perform the data augmentation trick. And so the baseline is to say I'm just going to use a count vectorizer and a logistic regression. That achieves a 0.79 accuracy. And the teacher that we're going to use to increase the performance of that student is a BERT pre-trained that we fine-tune on this same 1K train. And this gives test results of 0.89. We predict this 1K train probabilities. We also predict the unlabeled samples. And so we retrain our pipeline. And this time we have increased the accuracy by 8%, which I think is a great example of how knowledge distillation can work in this simple case. Note that instead of using a logistic regression like above, we're using here a linear regression because we're trying to match the logits of so we're using the logits method and we're trying to minimize the mean squared error between the logits of the student and the logits of the teacher. So in conclusion, we've seen that knowledge distillation can provide better regularization for training smaller models from the predictions of a teacher. And we'll also see that its applications to multitask learning can improve the scores. So yeah, we'll make the video available on YouTube. You can subscribe on our channel and or follow us on Twitter for later updates of further NLP breakfasts. And if you want to present your own paper, you can send us now an email at nlpbreakfast@feedly.com. Thanks for listening.